My name is Paco Jain, and with me today is Oleg Marichev. And we collaborated on this talk, which is about integral transforms. The title is New in Generic Integral Transforms. Before we get started, I'd like to introduce and also thank Oleg for the years of collaboration that we've done on this project. It's been really interesting work. Oleg is a mathematical, what I would consider a mathematical genius, comes from the Russian school, has 2 PhDs, in the Russian system. After you get what we consider a PhD, there's another level beyond that, has trained many mathematicians around the world who are professors and has many students, published many papers, and is the mathematical mind, I think, in the inspiration behind this project. For my part, I've been doing the coding aspect, more focused on the computer science aspects and getting these things into a form that's deployable, usable by people all around the world. So without further ado, let's get started. So today we're going to be talking about functions that are exposed in a packlet. If you've worked with the Wolfram language, you probably know what a packlet is. If not, it's just a system for distributing code in the Wolfram language. And you can click on this link that I've got here on this slide to go to the documentation page for this packlet. It's part of the Wolfram language packlet repository, and it has several functions in it. You can look and see a basic description of some of them here. The documentation isn't as extensive as we would like, and that's one of the things that in the future we will definitely endeavor to improve upon. But in order to install and load the packlet, the important thing is in this gray box here. You can click to copy these items and paste them into a Wolfram language notebook, like I've done here, and then evaluate them, and you should get the packlet loaded, and that should be all you have to do to execute any of the code you see in this talk. One small note is that the most up-to-date version of this packlet is 1.14.9. I'm not sure why I'm not getting that version. This version was just from earlier this week. There have been a lot of developments in the leading up to this conference. I just also want to point out that because this packlet is now, once you download it from the Wolfram language packlet repository, the code lives now on your local system, and you can go and look at those code files. They're all, so I've just looked, I've used this command to find the location of the packlet on my machine, and then I system open that location to get this directory, and you can see that the code is here in the kernel directory. Let me try one real quick thing. I wonder if, no, so I don't have a more current version in that location. If you do happen to be, once you're able to get, sometimes the packlet system is a little slow, so maybe later today or tomorrow, you'll be able to get the most up-to-date version, and that will include a directory called talks and demos or something like that, and or talks and papers, and you can actually find a copy of today's talk, this notebook, and some other talks from previous years, in case you'd like to look at those, are in that directory. All right, moving forward. So I'm going to hand things off briefly to Oleg to give a little primer on some of the mathematics behind the MyRG and FoxH functions, which are the special functions that power all the technology you'll see today. And he'll give sort of a mathematical introduction before I go through and show what the code can actually do. So without further ado, here's Oleg.
Hello. I'm happy to describe basic moments connected with super functions MyRG and FoxH. I've published my first book about these topics in 1978. It was translated English, and then we published 5 volumes, integrals and series, with the biggest the world collection mathematical formulas, integrals and sums. Later we published a book about fractional integral differentiation with Samko and Kilbas, which right now translated to Chinese is 1,000 pages book. And all this devoted includes a lot of integrals and much more. If we look on structure existing popular mathematical functions, you find that practically all significant functions are cases of super functions, which you see here. It is Meyer G and FoxH. And you see here that Meyer G, particular case of FoxH, when second parameters alpha, betas equal 1. Go down a little. And we can present examples how functions which you see here, it is a function exponential sinus integral n hypergeometric function can be evaluated into Meyer-G form. They representable through Meyer-G or through FoxH, and it gives us opportunity to unify absolutely everything. And instead, you see also that we have list of functions here. You see a list 170 functions, which are cases of this Meyer-G and FoxH functions. We can evaluate, and you see, no, we will not evaluate, but below you can evaluate and see how to represent all these functions through Meyer-G and FoxH. It means that if we have power and make integrals from products of this FoxH Meyer-G, we will be able, in particular, evaluate integrals from these products of these functions which you see here. And we already made tests. It's about 10,000 cases, which is a combination of these 170 functions. And if we will look on integral transforms, it means integral transforms from one of these functions, for example, Laplace, Meyer, and some other has in kernel such function from presented list. And you see here, right now, kernel, Bessel-G kernel of Hangel transform. And we have here literal hypergeometric. It's new function in mathematical system. We can evaluate a lot of integrals, and if you go to handbook published in 300 years, you find about 80% such integrals evaluated there. Cases of integrals which we are talking right now, and corresponding transforms also Stieltjes, Meyer, Hankel, Laplace, Fourier, also cases of this. Paco will continue my talk. He will present examples more detailedly, and I am giving you a right to talk.
Thank you, Oleg. All right, so let's go on. Oh, that's the wrong slide. Next slide. All right, so as I said, this code, these functions are all exposed through a packlet called Special Functions in Calculus. And that Packlet exposes 6 Wolfram language functions. So we have first a function called sample univariate functions. This simply produces a random function. You can look at the documentation page for the resource function of this. You can see that evaluating it gives you just a whole bunch of different sample functions to use, say, for inputs to these integration routines that we'll talk about. So let me find one that looks interesting. Okay, here's a rational function. I'm gonna, oh, interesting. I've never seen those error messages before. Okay, so this is one of the dangers of live demos, but you see that the answer came out. We got a result in a MyRG form. Let me find a different function that doesn't throw quite so many messages. We'll just take this one. It's pretty simple. So MyRG form there consists of 2 terms. You see that these MyRGs are grayed out. That's because they're inactivated. If you highlight them, you can see that inactive wrapped around the MyRG. That's just so that the MyRG doesn't immediately re-expand into simpler functions, right? Because we want it to be in this
Frozen.
form. Yeah, it's a frozen MyRG so that we can act on it later as a MyRG without it simplifying. We can also do FoxH function, the FoxH form. FoxH form is related to the MyRG form in a simple way for most functions. So those are, that was my second bullet. So basically, whenever we operate with these later functions that I'm going to talk about, we're first going to convert the input function into MyRG form or FoxH form. So the steps are, you have some input function that you're interested in. You could either have, most of the time, you're going to have your own function from the problem that you're doing.
It's too simple,
but
make more complicated.
But in this case, okay, Oleg wants a more complicated function. Let me make it not quite so complicated. Okay, let's try this one. That one was too hard to do. Okay, let's try this. So you can see that there are some functions which we can't convert, but as Oleg says, not only those 170 special functions, but any sorts of combinations, compositions, additions, multiplications of those types of functions can allow them to be converted into MyRG or FoxH. Once we've converted them to MyRG and FoxH, we can do all kinds of things with them using the properties of those functions. For instance, we can calculate integrals in a simple way. So we have another function exposed by the Packlet called GenericIntegralTransform, which is just like the system integrate, but it uses this MyRG technology, Fox/FoxH technology, and it can do integrals that the system integrate cannot do yet, and it can do some integrals a lot faster than the system can. And we'll talk some about that later, although not in full detail. And then we can, oh, interesting. The function expand didn't happen to work on this MyRG, so there's maybe an ill-formed MyRG. I will say that this this code is all sort of bleeding edge and has been developed on a daily basis for years, and so
not each function can be convertible to MyRG.
And occasionally there are still some bugs which we're working out. The next function I'll talk about is fractional order D. We've talked about this function at some of our other WTC talks, and it is like a derivative, but it can compute fractional order diffeo-integrals. If you're interested in knowing what that's about, you could see one of our previous talks. And then finally is GenericIntegralTransform, and that's what we're going to be covering today. Yeah, so let's move to the next slide where I can introduce the function GenericIntegralTransform. So what is an integral transform? Basically, the idea is you start with a function and you compute a certain integral of that function multiplied by what's called a kernel. Now, this kernel might be an exponential function that involves this. I should also say that the kernel is a function of the input variable that you're going to eventually integrate over, and then an output variable, which is going to represent the independent variable of the new function that you get as a result of the transform. And this kernel could be a variety of things. Like, let's say we're talking about a Laplace transform, which is one of the most common ones in physics and math. There, the kernel would be e to the minus tx here that I've highlighted. if you just call generic integral transform, as I've shown, with no arguments, then you get this display of the various transforms that are supported currently. And so here you can see how Laplace is defined, for instance, or how Fourier is defined. The Fourier transform is another one that's very common in math and physics, and you can see it has also an exponential, but this time with a complex exponent. Anyway, so we have right now 14 transforms that are exposed, and we'll be working going forward to add even more. But we've got, I think, some of the most important in the physical sciences, mathematics, and so forth. I'll just evaluate these all at once. But this is just demonstrating for a single integrand, for every transform, we see what kind of results we get. We can see that the results are usually in form of an inactivated FoxH or an inactivated Meyer-G. Occasionally, for some of the transforms, Kontorovich-Lebedev is not working. Don't know what
No, it's not working.
It was working earlier, so I don't know. But anyway, you can see sometimes you get, like in this case of the Weil transform, you don't get FoxH or Meyer-G. But for the most part, you do. So I'm not going to go into too much justification about why you might want to do an integral transform. That's sort of, I think, beyond the scope of our talk. But suffice it to say that it's a certain defined integral of a function that can be useful for, say, solving a differential equation, or there's all kinds of uses for these things. So now let's focus on one particular transform, just so we don't get lost in the forest of all 14 of them. We're going to talk about Laplace. Again, it's maybe, if not the most, maybe one of the top 3 most useful transforms. And as part of our Packlet, we've got a collection of 10,146 functions where we are able to calculate Meyer-G forms, FoxH forms. And so that's a good collection for us to test our integral transforms on. So here you see the results of such a test. Amongst those 10,000 functions, when we try and do the Laplace transform, you will get 97% results. That's what this purple with result label is meant to indicate. And another important thing to see is how long it takes. You can see that on average, these are taking about 45 milliseconds. So very fast, especially compared with the built-in Laplace transform and the built-in system integrate, and also much better coverage. Incidentally, if you want to be able to access these 10,146 functions that these are tested on, you can do sample univariate functions, all, and then you need function type goes to medium test set. And if I do this and measure the length, it takes a second or two for them to load. Oh, messages again from some ill-formed Meyer-Gs, but you can see that there's the 10,000 number I talked about. Okay, so one interesting and useful thing about these transforms is that when you can perform a transform in one direction, and then so you start with function A, you perform an integral transform to get function B. These things are reversible. You can perform an inverse integral transform to get from function B back to function A. And if you do these 2 operations, you should get back to where you started, is the idea. And that's something that that's a property that our function supports. So we can do this generic integral transform with Laplace. And here the x and the z, so in is just the expression that I'm doing the transform on, x is the input variable, s is the output variable, and then the fourth argument is just the particular transform that I'm interested in this case, Laplace. So I evaluate that. You can see I get a result in terms of some hypergeometrics and gammas and things. Okay, so testing the round tripping, I'm going to take this result that I just got and perform a Laplace inverse transform. I called it Laplace inverse rather than inverse Laplace because then alphabetically they come next to each other. Just a little thing. Okay, so So here's the result of the inverse Laplace after I activated it. In other words, after I let this FoxH expand into simpler functions. You can see it involves some array functions like the one we started with, but until I simplify it, it doesn't look like the original expression. But indeed, you can see here that when I simplify it, I get, here's the input expression, here's the result of round tripping, and you see that I get the same. Another thing we might be interested in is to see how we do in comparison with the system Laplace. I promised you that it was better, faster, that sort of thing. So can we show this? I'm not going to do this as a live demo because Laplace transform in the language is so slow that this, I picked 100. I picked a random set of 100 of those same 10,000 functions we saw above. It would take about 20 minutes to run this test, but I basically, here you see a grid where I have the input function, the result of the built-in Laplace along with its timing. This first element of this list in the right-hand column is just the time it took. And I put a time constraint of 15 seconds on the calculation, so many of them come back aborted after 15 seconds. So let's summarize how these results look. You can see them in the table, but just to give you the sort of headline, when we look at these results, we see that the average time taken is 10 seconds. That includes a lot of the ones that were aborted after 15 seconds. But even the ones that complete and return a result can take, several seconds, 6 seconds here. And remember that the code that, or when I ran the tests on these same functions, the average time was 50 milliseconds as opposed to, say, 10 seconds, so quite a bit of a speed improvement. We see that the system Laplace, out of 100 of the 100 inputs we tested, 47 of them aborted after 15 seconds and weren't able to come up with a result. Amongst the ones that did come up with a result, amongst the ones that didn't abort, 24 of them returned unevaluated. So in other words, they were not free Q of the Laplace transform function. 24. So amongst the 100 functions, the only about 25, maybe 28, came back with a result, and we did 100% of these functions, so, or 97%, depending on which sample you take. So that's quite a bit better. And then finally, another sanity test to make sure that we're doing things right. Kind of when you do integration, unless you have a tricky function that's maybe jagged or rapidly changing, kind of the ground truth to know what the value of that integral is could be numerical integration, right? Because the numerics don't really care how complicated a function is. So for instance, if I take a random input function and I do the integral, the numerical integral, we're gonna be a little bit sloppy and ignore some of these messages, but hope that the integral did evaluate correctly. We'll do the Laplace transform and look at, and I'm going to replace, so this value of S was the one I stored above, which was the, let me find it above here. I had to, in order to do the numerical integration, I had to pick a numerical value of the output variable. So I just picked a random complex and stored it as S, capital S, or lowercase s, no formal, not formal s. And so when I make that substitution, you can see that, yes, indeed, I do get numerically equivalent results. Only in this case, I had a nice analytic expression to, before I even had to numericize. So that's really awesome, I think. All right, moving on to the next slide. That's pretty much all I wanted to show today. There's a lot of work left to be done, continuing to test, benchmark, and debug some of these functions. They're not all working perfectly yet, but we're getting better and better by the day. Some of the next features we're going to be adding are conditions of convergence. So you notice we kind of assume that these integrals converge, but there's cases where you might get a formula, a result using these techniques, but that result is not quite correct because actually the integral doesn't converge at all. So Oleg has already developed almost all of the framework for returning conditions of convergence, and it just didn't come together in time for today's, for this conference. We want to be able to handle distributions because those are pretty important in these types of problems that you might address with integral transforms. So like handling things like Dirac delta will be important, which right now we don't do so well. As I said, we're going to continue testing, benchmarking, and debugging these so that as our results get better and better, they don't, we don't lose old results that are good. And then last but not least, we're going to improve the documentation so that these are easier for everyone to use. So that's all we had to speak about today. And
yes, I can add several words. I placed at the end of notebook a list of literature which can be useful for beginners who are interested to study what and how can be evaluated. Can you show this?
Yes.
Yeah.
So here you see, we have biographies for Oleg, his various works, and some other links that of interest.
I talked several times even on the internet, and I published 12 books. A recent book, handbook of Mellin transforms. Mellin transform is a key transform, and it is actually equal to Fourier transform, which people studied everywhere in colleges. By changing variable, we can convert without losing genericity Mellin to Fourier and back. We have nice information about this in Wolfram function site. People can find there. No, thank you.
Yep.
Do you have questions?
Yeah, so there's some live Q&A questions here. I'm going to try and answer a few of them. First question, can Oleg provide links to his books? We just saw that. Saw the links there at the end. It's on the last slide of the talk, so yes. Another question, what does the dot under the variable name mean? So in Wolfram language, if you use what's called a formal symbol, then that's a letter with a dot above and below the letter. And those are symbols to which you cannot assign a value, and they can be useful for representing things like, say, the dummy variable in an integral or something. If you want to know more about formal symbols, you could reference the document.
Add, several words. We have technology which allow to evaluate formulas with generic parameters like mn per q for Meyer-G function and for other functions, not only for concrete functions. What else? Question?
What are the statistics for the native Laplace transform function? Okay, so as I said, I don't know exactly what statistics are being talked about there, but a random sample of 100 that I showed you before, about 28% were completed.
You remember Michael Trott presented the most list of the most popular transforms. Fourier is the most.
That's not what the question is, Oleg.
Yeah. Okay. What else?
All right. That's all. Thank you very much.
Thank you.